All right, good afternoon, everyone, and welcome to ZEIC's Decarb Lunch series. My name is Mariko, and I'm the Program Manager for B2E at the Zero Emissions Innovation Center, also known as ZEIC. I'd like to start this webinar off in a good way. I'm joining you today from the traditional and unceded territories of the Musqueam, Squamish, and Tsleil-Waututh nations. We respectfully acknowledge that our staff and collaborators live and work across British Columbia and on the territories of many First Nations who have stewarded these lands and waters since time immemorial. Today, we have the Decarb Lunch, less oversized, more decarbonized hot water and MURBs, with speakers from Introba and SES Consulting to talk about best practices in designing domestic hot water retrofits in multifamily buildings. Domestic hot water contributes to a significant amount of GHGs in existing residential buildings because they typically use fossil fuel boilers. Retrofitting these systems with heat pumps can result in large emission savings with minimal tenant disruptions. If you have questions for the presenters today, please engage in the chat. It's also a place to connect with the audience and we'll add some relevant resources or events and provide comments. And we'll draw from this commentary in the chat to help guide the panel discussion at the end of the webinar. I'd also like to thank City of Vancouver and BC Hydro for their financial support. Their support enables us to continue offering webinars that are continuing education accredited for free. And my colleague Victoria will drop some details about getting continuing education credits for attending today's webinar in the chat. And please make sure that you submit for credits as soon as possible. So before we dive in, I wanted to give a brief intro into the Building to Electrification Coalition. We are a BC-based coalition focused on supporting our members to facilitate a speedy transition to building electrification. And by connecting members to share best practices and find solutions to potential challenges, together we increase the capacity of the industry to achieve deep, immediate, and real emissions reductions through electrification of building systems. Joining our community is simple and free, so please visit our website for more info. Lastly, before I pass it over to my co-host, I'd like to remind everyone about a recently published update to the BC Building Electrification Roadmap. I encourage you to download a copy if you haven't already. Today's webinar fits into a few of the recommended actions in the BERM, including ensuring building systems are high efficiency, requiring performance commissioning, and developing performance standards for dual fuel equipment. You'll hear a little bit more about how those things could be integrated as we chat later on. So now I'll pass it over to my co-host Robin to share a few words about AEE Metro Vancouver.
Thank you, Mariko. So yes, thank you for the introduction. So AE stands for Association of Energy Engineers, and we have our local chapter, AE Metro Vancouver, and we're a local chapter where energy enthusiasts are meeting together. And so if you go to the next slide, I will give a little bit of an overview of all the things we try to do and create a community. So I see a poll there, so let me check if I can reduce that, move that poll here. So but our chapter has a couple of things we try to do. So we have mainly our events are what's very important. We try to engage with local property managers, engineering companies, and instead of showing just YouTube videos, we go to real installations, we show equipment, and it creates a community where people can engage with each other, talk with each other, learn from each other. So we strongly engage that you join our chapter. It's volunteering groups, it's all for free, and it's an amazing opportunity to connect and make friends and learn from the industry. There's still the poll in front of the next slide. Yeah, so just an example, how can you follow us? So we have a mailing list where people can get updates of our events. And we have also our LinkedIn page where you can every month see what we do. There's lots of cool opportunities to learn from it. So if you want to know the next events, join us on our LinkedIn page or send your email address and we will add you to the list and you will be updated on the regular events. Thank you very much.
Thanks so much, Robin. So I just wanted to introduce our first presenter today. Harriet Lilley is an associate at Introba and brings over 12 years of engineering design consulting experience to Introba's climate team. She has extensive experience in supporting organizations in decarbonizing their portfolios using quantitative analysis to inform strategic decision making. So Harriet, please go ahead and you can start your presentation.
Perfect. Thanks, Mariko. Thanks everybody for joining us today. I'm going to take you through a case study that we completed last year. But before I jump into the details of our study, I wanted to kind of zoom out and ask the question, why are we focusing on domestic hot water and why is it important? Domestic hot water systems are often perceived as a relatively small load and are often the last remaining system on natural gas in buildings. So will decarbonising these systems really move the needle on emission reductions? We believe the answer is yes. These systems represent 35% of residential emissions in BC. So while domestic hot water is frequently overlooked or maybe underestimated, it's actually a critical piece in the decarbonisation puzzle. And through our findings of our study, we hope to show you that domestic hot water electrification is cost effective, practical, and really a low-hanging fruit that's yet to be picked. So before I jump into the details of our study, I wanted to give you a bit of background and context for the study as well. So in 2024, myself, Stuart Hood and Introba developed a design guide for domestic hot water heat pumps and new MURBs for BC housing. And the guide really focused on addressing major knowledge gaps within the industry and highlighting best practices through case studies reviews. And the intent was to create a user-friendly resource for industry and build more confidence in adopting these systems in new construction. As part of the study, we completed a thorough literature review and a number of subject matter expert interviews. And a key element kept coming up through these interviews. And this was that domestic hot water consumption is a key input into designing these systems, but the industry guidance out there is not very consistent and varies widely. And with engineers typically leaning towards more conservative assumptions, we started to ask the question, are we oversizing these systems? And is there an opportunity to optimize the size of these systems through measured data? This led us to partner with B2E Committee and explore our retrofit case study, which I'm going to take you through today. And the study first looked at comparing traditional versus new sizing methodologies for the domestic hot water heat pump systems, and then how measured data could be used to optimize the system further and remove these perceived barriers to entry around these systems. So our case study focused on Guildford Court. This is a low-rise rental MURB in Vancouver's West End. It has 67 occupants of a mainly senior demographic, so relatively low occupant density, and 44 suites. The existing system in place is 2 atmospheric domestic hot water heaters with a natural draft flue, and then the space heating system is also a gas system. The kitchen and laundry are all electric though. Important to note that each unit also has a gas fireplace with a standing gas pilot light as well. So when we looked at the total energy use and the greenhouse gas intensity, we could see that the domestic hot water system was actually quite a large portion of the pie. So about a third of the total energy use of the building and 44% of the GHG intensity. So our first step in the study was to explore sizing methodologies. So we have our traditional fossil fuel sizing methodology, such as our ASHRAE or ASPE, which I know a number of us have been kind of taught to size these systems on. And these really are designed for these systems using the sizing methodologies are designed around that higher output and rapid recovery with minimal storage. Whereas with domestic hot water heat pumps, we generally use EcoSizer as that kind of leading tool that's been developed alongside this technology. And with the domestic hot water heat pumps, we focus on prioritizing that thermal storage with that lower thermal output. And this is really around those heat pumps are the most expensive part of the system. So you want to size those to really the average load and use that storage for the peak of the system. And it's typically a 4-to-1 ratio of increase in storage and decrease in thermal output. So when we look at these two approaches and we're using them to size the domestic hot water heat pump systems, we can see that if we use those traditional methods, so ASHRAE and ASHRAE, it would be kind of a no-starter in terms of the size of these systems. We're coming out with very large number of heat pumps or very large number of storage tanks. So highlighting here that not to use those traditional fossil fuels methodologies. When we're designing domestic hot water heat pump systems, we should be using EcoSizer, which has been developed for this technology. And we can see with those kind of default assumptions around occupancy and consumption, we're coming out at 7 heat pumps and 4 tanks. So much more palatable, much more practical a design. But as part of the study, we wanted to really kind of the meat of the study was looking at how we could optimize this system further through measured data in this retrofit scenario. So as I mentioned earlier, within the industry, the assumptions around domestic hot water consumption vary widely. And we can see this on this graph that that's kind of a factor of 7 between passive house assumptions and ASHRAE assumptions. The EcoSizer sits around the 25, so slightly lower. And we can see some measured data studies as well available from the City of Vancouver on that lower end. So measuring the data, Riada Sales very kindly lent us a meter, and we installed this for 2 3-week periods over October and March. Ideally, we'd really recommend at least 3 months of data collection, if not 3 to 6 months, preferably. And to flag that commissioning is very important when you're setting up these meters for accuracy. In terms of the results of the measured data, it came out much lower than those domestic hot water consumptions that we're seeing in the industry guidance. So we could see that the average consumption was kind of 5 to 6 gallons per person per day, with a peak consumption around the 10 to 12. And just to note, in that October period, we were seeing the Canadian Thanksgiving weekend. So you can see that Sunday was right up at the 12 on the Thanksgiving. So where does this sit in terms of our industry guidance? Much further on that lower end. So really flagging that there might be an opportunity to kind of optimize the sizing of these systems, and we might be oversizing with our default assumptions. So when we plug those numbers back into the EcoSizer and we came out with the results of the size of the heat pumps and the size of the storage tanks, we could see that we could halve the number of heat pumps in the design. So a significant reduction and a much more cost-effective and practical solution. So through using that measured data on retrofit studies, we really feel that you can optimize that design. And in terms of what does that look like? Well, the traditional sizing methodology, as I mentioned at the start of the presentation, would probably be a no-starter with a huge array having to go on the roof, so some structural issues there. But when we optimize that design, we can see that it's really 3 of these small heat pumps, the size of a suitcase that could be placed in the parkade. So a very practical solution for a retrofit scenario, and with those 4 storage tanks as well, supporting that peak demand and some of that load shedding as well. One of the other key findings from our study was around how we approach sizing these systems when we don't have measured data. So typically, if we don't have measured data, engineers take the natural gas consumption in the summer as a proxy for the domestic hot water consumption. But when we translate that energy figure into consumption, we can see that we would be oversizing the system by a factor of 5. So our measured data, we knew that we had kind of an average consumption of 5 gallons per person per day. And if we translated this natural gas consumption into consumption of domestic hot water, it'd be up at that 25 point. And that's really representing all of the losses within the system. And something that we call out within that domestic hot water heat pump guide is minimizing those losses is really important when you're designing these systems in new construction as well as retrofits. To highlight that in a different way, we've presented the demand and then the losses within the system in the existing natural gas system versus the heat pump system. And we can see that the demand is the same. The heat losses in the distribution is the same. Heat losses in the tank slightly higher in the domestic hot water heat pump system as we're storing that at a higher temperature. But then within the existing system, we've got these losses from the inefficiency in the boiler or the heat, the gas domestic hot water heater, and then a huge amount of losses associated with cycling, flue losses, and potentially those pilot lights within the apartments. So we wanted to flag that as a potential portion of those losses is to do with the pilot lights as well. So a huge opportunity to reduce the energy associated with the domestic hot water system if we retrofit to these heat pump systems, showing approximately a 90% reduction in that domestic hot water energy, which translates to about 30% reduction in the total energy use of the building. So real opportunity to reduce energy there. And then when we look at cost, how does this come through? We can see that on a first cost basis, it is more expensive to install. So day one first costs are higher to install these systems. But we can see that through optimizing the design, you reduce that first cost. And a lot of that first cost is really around the installation. So on the when you're replacing the equipment, this would be much smaller. But because of those energy savings, we can see on a net present cost, so a 25-year period, we're actually cost neutral in a business as usual case where you're replacing your like for similar system compared to your optimized heat pump design. So a very strong business case for a practical and cost-effective retrofit scenario that really significantly reduces your emissions by a significant portion. So key takeaways from the presentation: EcoSizer is the design tool to use for domestic hot water heat pump systems. Measured data is critical for right sizing. So if you have the opportunity, install the meters, collect the data, and right size your design. And this really presents practical and cost-effective system designs that are easy to implement and install. And finally, just to kind of flag, domestic hot water retrofits are scalable and can be high impact as the key takeaways. And I'll end there. Pass back to Mariko.
Thanks, Harriet. Great presentation. I did want to emphasize too that this case study was based on an existing building with an occupancy that might not be typical of every single residential building, with having a lot of seniors, et cetera. But it's really interesting to see the difference between the measured, the ASHRAE sizing, EcoSizer, and measured, because there was significant difference in all of them. Robin, did you have a question for Harriet at all?
I will ask first the question in the audience. So when you measure the consumption, is it to find the peak or the average or both? That's a question.
Yeah, both are important. So you want to find out both of those numbers. We could see that both were quite low. So we had 5 to 6 on the average and 10 to 12 on the peak. So we took the peak to design on the EcoSizer. But really, you'd want to look at the data. And as Mariko said, it's a senior occupancy. So those numbers are slightly lower. And we've seen in studies that with student housing, it's much higher than that.
Yeah. I have another question. So in the audience, we have multiple people here. So, but if you want to implement the concept, how would it be for the audience to look at the stakeholders to implement that? Do they start with an energy audit? Maybe it's in the regular capital planning. There's a property manager who is an energy enthusiast. Is it because of GHG reductions and regulations? How would they start with the implementation of such a system?
Yeah, it's a great question. I would say so from a property manager perspective, is that?
Yeah, I would say like that, yeah.
Yeah, I think it's talking to the Strata Council, always starting with them, and then seeing probably contracting a consultancy to kind of take you through the design, guide you through the process. I know with a lot of the retrofits, there's these concierge programs, the different advisor programs that can help you through that process as well. But I think, yeah, having someone on board, a professional to go through the sizing of this and selection. And then the manufacturers are excellent as well and will support the process um, through that.
Thank you very much.
I'd say another comment in the chat that Fresco did a flow measurement in a MURB and their peak gallons per day came in around 17. So I think that emphasizes the fact that measured data is always better in an existing building.
It is, yeah. I think also just to highlight when we sized it, so we had 12 as our peak. We did the design for that and it was pretty low. And so we added up, we took it up to that 16. That was the City of Vancouver study that found that 16 was that sweet spot. So similar to that 17 as well, but a lot lower than the default. So the default is 25 in EcoSizer, and ASHRAE obviously a lot higher. Any other?
Yeah, one more question from the chat. So what was the cost or effort of getting 3 months of accurate domestic hot water flows? Is the equipment needed fairly standard? Um, and
Yeah,
yeah, any
that's
elaboration?
a great question. As one of our kind of key takeaways was from the study was to look at potential like incentives or support for hiring of this equipment through different channels. We were kindly lended the equipment to implement. So I don't know the cost figures off the top of my head, but it's something I can follow up with. I can see that's from Sean, so I can follow up with you on that one.
Should we still ask the other question here,
Yeah, I think we have
Mariko?
time for that, and then we'll move on.
Yeah, so somebody asked, I'm curious about the distribution system temperature targets. Lots of discussion in co-development in Canada in terms of Legionella. Does domestic hot water recirculation system run at 140 degrees Fahrenheit?
Yeah, so Legionella is not a concern with this system. The heat pumps actually raise the temperature up higher than typical systems. So that's why we have that higher loss within the tanks. And we have the swing tank obviously taking care of the temperature within the distribution system as well. So Legionella is not a concern with the system. The heat pumps really raise that temperature up to 70 degrees C. So no
Okay,
issues
thank you
there.
very much.
That's great.
Yeah.
Thanks so much, Harriet. We'll have a chance to chat with you again later, but we'll move on to a presentation from Brad White. He's a professional engineer with over 15 years experience in energy efficiency, low carbon technologies, and smart building systems. He's also the president at SES Consulting. He demonstrates his passion for sustainable use of energy throughout his professional career, and this continues to be a driving force in his work. So, really interested to hear about your presentation, Brad, and a real life installation of a domestic hot water heat pump system.
Yeah, thanks, Mariko, and thanks, Harriet, because I think you set the stage very nicely for what I want to talk about today. So, and some of you, if you've been hanging around decarb lunches and reading B2E case studies, you may be familiar with this project at Fraser Point One. I'm going to give sort of a different perspective on the project than I have in the past, but certainly you can go back into old case studies and recordings if you want to sort of get a more in-depth review of kind of the retrofit itself and the design process, because lots of interesting lessons there. But this project was done, I think, completed 2023, I want to say. So it's been in operation now for a good couple of years. So we've got some interesting results in terms of energy savings, but I also really want to kind of dive into that sizing piece. And I've recently been kind of digging into that data and just some interesting takeaways that at least I haven't heard talked about a lot. So hopefully it'll be to the benefit of some folks here. So with that, I will dive in. So a little bit about the building. This is a considerably larger building than the one Harriet was talking about. So this is a 15-story, might even be 16, residential tower, all rentals. It's owned by Concert Properties. It's located in South Vancouver, kind of adjacent to River District, sort of an older part of that city, of that part of the city. Not part of the new River District development, but kind of right beside it. Built in 1990. It's got 170 suites. Again, demographic very different than what Harriet described. A lot of the studios and 1 and 2 bedroom suites, a lot more families, sort of a demographic that very much skews younger, in addition to, kids and such, which has a significant impact on the consumption, as we'll see, compared to some of the numbers that Harriet was talking about. The suites are all heated with electric baseboards. So the gas usage that you see there is just for the domestic hot water and the gas-fired makeup air unit. And of that sort of 4,300 gigajoules, 3,200 of that we think is the domestic hot water, which is actually a revised estimate, revised upward from the number we had originally developed during the study. We did an energy study, I think almost 2020 now. I think we had about 2,500 gigajoules as being the domestic hot water consumption. Revised that upward as we kind of got more data on the building. So we think kind of 3,200 is about the right number for the domestic hot water, and the rest being just the gas-fired makeup air unit. So the original system that was there was I'll call it, kind of high capacity, low storage design, had sort of 2 big atmospheric super hot boilers that you see everywhere. They were 600,000 BTUs each. They had 360 gallons of storage, and as I said, about 3,200 gigajoules a year of gas consumption. That system was end of life. And so we had done a study just kind of building on that question. One of the last questions they were asked, Harriet, was like, how do we get to the retrofit? It's like, well, it was a combination of, we were doing a study, this system was end of life. Owner was motivated to reduce greenhouse gas emissions. And so that's kind of how we settled on a new system, which was designed as a hybrid between CO2 heat pumps. We have 10 CO2 heat pumps. We've got 5 120-gallon storage tanks. We've got 2 gas boilers, which are 200,000 BTUs each. And then we've got an electric, not a swing tank, but it's actually an electric instantaneous heater that's kind of maintaining the recirc loop. And again, I've got other presentations on sort of how we ended up on this design, what were some of the constraints. But, in short, there wasn't enough electrical capacity to go all electric. And so this hybrid design was kind of settled on as a way to sort of maximize the greenhouse gas reductions within the available electricity capacity that was remaining in the building. This is just this drawing of the building of the new system. You can see here, storage tanks, boilers, here's the electric heater, and then the 10 heat pumps. All working together, all DDC controlled. So the building had an existing building automation system, which is a little bit unusual for residential buildings, but we didn't have to install that, which was nice. So it was already there. And so we were able to make use of that to control the sequences of operation for this system, which, as you can imagine, are somewhat involved. But now onto the metering. So prior to design, we decided to do some metering. So we installed I think it was just an on-a-clock. It's a permanent meter. So this wasn't an ultrasonic. We actually installed a turbine-style meter connected to the DDC system to record the data. And so here's the results. So you can see, so the blue bars are sort of the average daily consumption by month. And then I've compared that to sort of the equalizer value, sort of the default equalizer values if you put in the same number of suites and occupants. And then the ASHRAE, and incidentally, the ASHRAE daily average is about the same number. And then the ASHRAE daily max is obviously quite a bit higher. So you can see we are not that far off the equalizer and the ASHRAE average values. We're kind of just under 6,000 gallons per day in the winter, and obviously we can see here much less in the summer, which one, I think is that just in and of itself is an interesting result because I don't think the seasonality of domestic hot water consumption is always appreciated in design. So there's a lot of emphasis on, yes, you need to meter, definitely put a meter in so you know the consumption. I rarely hear anyone add the caveat, make sure you're metering the right kind of year so that you're actually getting a true representation of your peak data. So for example, you can imagine if you were to come in the middle of summer and meter for a couple of months and then say, well, that's, apply that data to the overall year, you actually might end up quite a bit undersized for the winter consumption. And this data is backed up. I found an old study from New York City back in 1994 that showed a very similar result. And it's not something that I see talked about a lot. At least I haven't seen it. So it's one thing I kind of want to emphasize. If you think about it, the reasons for it kind of make sense. If you think about you're having a shower and you like your shower at 110. Well, in the summer, that might be 70% hot water, 30% cold water to kind of mix to get you at 110. Well, in the winter, and I'll just skip ahead a couple of slides, I'll go back, but the incoming water is much, much colder. You can see this is the Vancouver domestic cold water temperature profile. So you can imagine in the winter to get that same 110 shower, now you might need 90% hot water, 10% cold water, right? So not only do you have much colder water that you have to heat up, but you're also going to be using more of it if you're mixing to kind of get the same temperature. And so I think that's, those things combined to give you, obviously a much, almost a third higher consumption in the winter versus the summer. And so if you look at that kind of on a daily profile, which is what we did here, and this is just for the past year, I kind of went back. So the highest daily consumption is 7,200 gallons, and that was a Sunday in January. And that wasn't, it was the highest single day in the past year, but Sundays in January tended to be quite high. They were all, well over 6,500 gallons per day throughout that month. And, again, go back here, it kind of stays similar through kind of January, February, March. And then if you want the lowest daily consumption, that's a Friday in August, and it's less than half of what you see on that Sunday in January. So, kind of interesting to know that, so that if you are doing that metering, you actually come in and meter at the right time. So what does that end up meaning for our system energy use? And so this is an energy use profile for the new system. We had the benefit of having the electricity for this plant sub-metered, and then I just kind of manipulated the gas data a bit to get it, the boiler gas data in a way we could kind of visualize it. But so this is the energy coming into the plant. So you can see it's kind of dominated by the boilers. The energy used by the electric reheat and the heat pumps, they stay pretty consistent year round. And then the boilers, you can see we use a bit of boiler in the summer, but we use a lot of boiler gas in the winter. Again, because the consumption is much higher. So all of that peaking is kind of handled by the boiler. But if you might look at this and say, well, are the heat pumps actually really doing anything? And the answer is yes, because if you look at the energy output, so this is essentially taking that coefficient of performance, and I've kind of used the seasonal profile based on average outdoor air temperature, because the COP is obviously, it's going to be much higher in the summertime than the wintertime. So if you take that and so you translate these numbers into the output. So this is the energy coming out of the domestic hot water plant. You can see now it's actually dominated by the heat pumps, and then the boilers. Again, they're doing a fair bit in the winter, but the heat pumps are still doing the majority. And you can see the electric swing tank kind of does a very consistent. I mean, it's an electric resistance element, and the energy used by the recirc loop doesn't change all that much throughout the year. So it's a pretty consistent base load on the system. And then you can see the heat pumps and boilers are much more seasonal and how they operate. So I also ran through a sizing comparison, just looking at sort of what was there originally, plugging the numbers into EcoSizer, because as Harriet says, it's a pretty good standard tool for this kind of plant. And again, I just used the default assumptions. I didn't, you can actually do a fair bit of manipulation with the Equalizer if you play with it, but I just used sort of the default assumptions to see what it would come up with. And then you have our actual plant size there. So you can see the original was obviously huge, like way more BTUs than we actually needed, even with the lower storage. It was still, probably not, maybe not quite double, but almost double what we needed. We put the numbers into Equalizer, and again, you can there's a slider where you can play with the storage capacity. So I kind of minimized the storage capacity to mimic our system because we had very limited space for storage tanks. I mean, we would have loved to have had, 6, 8, 10 tanks, but we only had room for 5, so we had to make use of just the space. That's all the space that we had available. So Equalizer came back with about 600 MBH total, so kind of 500 heating. And Equalizer doesn't tell you whether that should be heat pumps or whether that should be boilers. It just says, here's how many BTUs you need. And then here's the swing tank, what you should have for your swing tank based on what its estimates of the losses are. And then here's how much storage. And so then we can compare that to what we actually had, which was 400 MBH of boilers, 154 of heat pumps, and then about 40 MBH in the swing heater, that electric resistance heater, and then 600 gallons of storage. So ended up being quite close to the Equalizer results, which I thought was interesting. So I would say overall, it did a pretty good job in getting the sizing right. Even if we kind of jump back, and just another observation to point out here is we actually are. Our peak, as I said, was 7,200 gallons a day. It's actually higher than what Equalizer estimated in this case. Now, that may be because the occupancy numbers weren't quite right. I don't think we actually knew exactly how many people were in the building in the various suites, so we had to make an estimate. So that's potentially one source of error where maybe we had used a fewer number of the number of occupants I used for Equalizer were less than perhaps what was actually in the building, for example. But then also just comparing to some of the numbers that Harriet presented, as she was talking, I was kind of crunching the assumptions of, anywhere between, let's say, 250 and 350 people in the building, probably. Our gallons per day are at peak are, 20 or more. So double what was found in Harriet's building. So I think again, and I think there were some other numbers that the Fresco provided. And so I got to think this building's probably near the top of what you would see in practice, but I think just kind of further underscores, it's not a good area to make an assumption on, and that metering is invaluable because obviously the implications for sizing are radically different if you have, if you get a peak of 10 or 12 gallons per day, or 16 or 20 or higher, right? That's going to significantly impact the size of the system you need. So the metering is crucially important. In terms of the energy savings, what we ended up with, so going from the study phase, we estimated about 2,000 gigajoules per day and an increase of about 124,000 kilowatt hours. What we actually saw this is again over 2 or 3 years of actual performance, is we've reduced the building gas consumption by about 2,600 gigajoules. And that's out of 32 that we were originally using for the building. And again, some of that is because we've shifted the load of the heat pump. Some of that is just because the boilers are now way more efficient. So that's not all heat pump. Some of that's just more efficient boilers. And then we've increased the electricity use by 170,000 kilowatt hours per day. So both of those numbers are about a third higher than what we originally estimated. And just, to kind of wrap up here in terms of takeaways. So the big successes from this project are, the gas savings have exceeded expectations. The heat pumps have worked fantastic. We've had very, very few issues with the heat pump. I think the biggest issue was some condensate freezing when it got really cold a couple of years ago. And, they just kind of set someone up to chip that away. And that was the extent of the intervention needed. Heat tracing was looked at, but it was very expensive to add at this point. So they decided to just kind of handle that manually. And I'll say the investment that we made into the controls, so having it all controlled by the building automation system, having that metering in place, That's been invaluable during the commissioning and troubleshooting process. We got a lot of scrutiny of the system from the City of Vancouver Plumbing Department. And so we were able to kind of provide extensive trend logs on all the tanks and kind of all that to satisfy their concerns about Legionella risk, because it's sort of the first system of this kind I think they had really looked at in a lot of detail. At least that was sort of the message they gave us, is that this kind of hybrid systems wasn't something they'd seen before. And so understandably, they wanted to be cautious and kind of have the data to back up the performance. And we were able to provide that because we had it all in the building automation system. And then we had to do some troubleshooting during commissioning that, again, having the data from the building automation system was, it would have been very challenging to do without. In terms of, after 3 years of operation, what have we learned? The biggest issues we've experienced have actually been with the boilers that have had occasional outages, which, just with the way the system is designed, has led to some complaints and loss of hot water on occasion. So that some of that's being rectified now with adding some after the fact control valves and things like that weren't part of the original system. The complexity of the system has been a challenge. Just especially as there's regular turnover amongst operation staff, so keeping people up to date, being able to provide them the information so they understand how the system is supposed to operate. That's sort of been something we've had to do on an ongoing basis. It's not the kind of system you can just walk into without documentation and understand how it's supposed to work. And so, ongoing work on that knowledge transfer piece, sort of as the system matures and as staff kind of goes through cycles of turnover. So, yeah, that's about all I wanted to cover today.
Thanks so much, Brad. Really interesting takeaways, and it's always great to hear about projects after they've been implemented. And there are some questions in the chat, and one is related to the system energy use profile. So I think you mentioned that you would have had, I think it was a use one, that you could have used more storage tanks. So I guess maybe I'll combine two, because there was another question around.
Yeah.
Sean asked if you had looked into converting extra parking into water storage.
Not an option in this case because everything's up on the roof. So this
Right.
is a penthouse plant. So we were restricted to the mechanical penthouse space. And even to add additional space, there wasn't much roof space. We took up most of the available roof space with the heat pumps. You probably could have squeezed a little bit more on the roof, but that would have been very expensive. So this being a penthouse install created a lot of additional constraints that we wouldn't have had otherwise.
All right. Yeah, that's great. Like, so if you had, but say you had maybe a little more roof space, a little more electrical capacity, what might you have changed in the design to maybe utilize more heat pumps or?
I mean, more heat pumps and more storage. I will say we do make pretty good use of the heat pumps. Like if you watch the system trends, kind of late into the night is when the heat pumps finally cut out. So they're kind of running continuously all day as the water cycling out of the system. And then, it's a big, obviously, peak of here. We can see it here, obviously, that big peak of usage in the evening. And then, the boilers take care of some of that peak, and then they do some of the tank recharge. But then we kind of shut it down, and we usually have a couple of tanks left that we'd let the heat pumps recharge, and that usually takes them until 2 or 3 o'clock in the morning. The heat pumps will run, and then they turn off because the water gets CO2 heat pumps need a pretty cold incoming water, and so we just don't have any cold incoming water at that point. So if we had more storage and more electrical capacity. So it's just more storage, we could probably run the heat pumps a little bit longer. Maybe we could squeeze an extra 10 or 20% of the energy out of the heat pumps compared to what we have now. If we have more electrical capacity, obviously we'd love to put in more heat pumps. And I think that would be, we could probably find the roof space to squeeze in a few more. Obviously, there's also budget constraints. So it gets more expensive at that point too. So that was the other trade-off, is just kind of keeping the budget somewhat reasonable.
Thanks, Brad. Robin, did you want to grab a question from the chat, or do you have another question?
So you talk a lot about the storage, electric capacity, gas capacity, and so on. How did you look at the storage tank in relationship to demand response in the design?
It wasn't really a consideration. The design philosophy around storage was how many tanks can we possibly squeeze into this space? And we will squeeze in as many as we can. And I mean, you can see from the photo, they're in there pretty tight, the photo on the right, to the extent that replacement will be a challenge because of the piping, and it was a conscious decision to kind of get as many in as we can. And I would say that was the driver. There really wasn't much consideration given to demand response during the design phase. I think the idea was let's maximize heat pump use. Now, could you do some demand response? Absolutely. Like we've got the control system. If we wanted to temporarily disable the heat pumps and switch over to the boilers, we could. If you wanted to disable that electric heater and switch to the boilers, you could also do that, although that's would require kind of manually adjusting some valves right now, but you could automate that process if you wanted to. So there's definitely the potential to do demand response. There was kind of no incentive at the point. I mean, even the way this system is metered, they're not actually charged for demand on it. So it's the consumption kind of fits within a small general service. So they aren't paying demand. So there's no incentive right now, but in the future, if we wanted to sign up for the BC Hydro Demand Response Program, or there was time of day billing, then yeah, there's definitely the potential to do that. But it wasn't part of the original design.
So still a good question here in the audience as well. So what are the economics versus a straight gas replacement compared to an electrical solution?
I mean, I don't have all the numbers in front of me for the economics. I'll say, I mean, certainly this is more expensive. This wasn't a project done because it was the most economically cost effective. It was done as sort of, in terms of greenhouse gas reductions, sort of getting the amount of greenhouse gas reduction they wanted to get most cost effectively was the approach, right? So this was sort of this system struck a good balance between getting, we saved kind of 70% of the GHGs of this system. But that came at a price, right? It obviously would have been cheaper to do just the gas. The heat pumps are not inexpensive. Again, I don't have the exact numbers in front of me. The heat pumps were not inexpensive, and the just getting the electrical up to the roof, that came at a significant cost, no question. In terms of the ongoing operation, at we're kind of paying a fairly high price for electricity here because of the way it's metered. So it's small general service, and gas prices are reasonably inexpensive right now. But even at that, they're not. The system operation is kind of cost neutral to even a little bit positive, depending on the seasonality of it, right? Like summer, they definitely the COPs are higher, so depending on the time of year. But overall, it kind of works out that you're not really paying any more to operate. Are you saving a lot on operation? Probably not really. But is that a good outcome in this case for the owner? Yes. I mean this was done to reduce gas consumption more so than anything else. And then obviously at time of design, carbon tax existed. There were incentives from Clean BC. So the situation at the time this project was done was very different than the situation is now, just from an overall picture of the economics.
I just want to build on that and maybe invite Harriet into this discussion too. Like if maybe if you had more electrical capacity, what are the strategies that you'd use to optimize the economics in a retrofit project?
Yeah, I think it is through that optimizing of the system size design. So through that measured data, you can reduce the size of those heat pumps and the tanks required. So that's not only reducing your electrical service supply, but it's the spatial requirements as well. I think there's some hesitancy around these systems with the kind of implementation with the structure and things like that. But if we can reduce the size through that right sizing, that can really help with the economies as well. And then those heat losses, I think it's minimizing on those heat losses. So we kind of highlighted those are a huge portion of the existing system. And maybe haven't been highlighted as much in the past because it doesn't make such a big impact on the cost. But when we're doing the heat pump system, it's making those systems bigger if we don't address those heat losses. So addressing the heat losses within the system is really important. So the distribution, even the suite layout, so we're doing new construction and things to kind of reduce all those areas is very, very important as well. So,
Yeah.
yeah.
You can see that blue line basically represents the losses in this building, which I think are smaller than average just because there's a lot the suite density, but it's about half of what Equisizer would tell you is the typical losses. But you can see even here, it's kind of significant. Like it's not an insignificant amount of power, especially since that's often done with an electric swing tank. It's kind of challenging to use the heat pumps to maintain. It can be done, but often it's an electric swing tank, or as we did, an electric heater or gas to maintain that load, and it's significant, right? So I kind of agree with Harriet's points that those losses are often underestimated. It wasn't something we really touched. The distribution wasn't something we were touching part of our project, but I agree that it's a place to look at. And also at the same time, is there an opportunity to reduce the load through, water saving devices like, low flow shower heads, aerators, like has that all been done, right? Because anything you save there can ultimately help you, better get that size of the system down.
Yeah, I think in the study that we did, we heard from the system experts that the losses can be kind of up to 50% of that demand. So that's a huge amount. And again, it's just in these gas systems, so we weren't highlighting it. And within some of the modeling methodologies as well, we don't kind of calculate them, so we're not addressing them. So we need to take more notice of the heat losses as well.
Certainly in commercial, there are a lot of the load. I think residential, just because the domestic hot water loads tend to be higher, we find it's proportionally less. But if you're doing this project in commercial, like it can be, sometimes the recirculation losses are the majority of the load.
Mm-hmm. I
People are
just
only
saw
washing their hands.
Yeah.
I just saw a comment from Roberto in the chat around the reset pumps as well. And I think someone internally on our commissioning team was saying in a project they'd switched off their reset tank or had it on a temperature control so it wasn't operating continuously. And that really helped save energy as well. But he said, do the reset pumps shut down for a few hours each night to you, Brad?
No, not in this project. They were having issues with the recirc system, just maintaining, that was not really tied to our project. It was an ongoing issue, but just because of that, we didn't want to exacerbate any issues with the suites sort of getting recirc to them because they had some balancing issues with their recirc system. So, no, we didn't look at that. It's something we would really commonly do in commercial. I mean, it's easy just to shut them down or even to go on that temperature control. But no, for this project, we didn't just because it was sort of we were risk adverse and owner was already nervous about the recirc system. So we left that alone. But you could.
When we were preparing for this, we were talking a little bit about challenges with the hybrid system. And Brad, you mentioned that there were a few boiler issues. So I was just wondering if you could surface anything around that and any recommendations that you'd have.
Yeah, I mean, hard to know how much is specific to the exact boilers we had, which were kind of a new product at the time, and how much is that would be sort of generally applicable to boilers. But certainly the complexity of the system creates some challenges, and just sort of not. Yeah, I think we paid a lot of attention to what would happen if we lost the heat pumps and making sure we could maintain the system without that. I think there was maybe less attention paid. Oh, what happens if the boilers go down? I sort of on the assumption that the boilers would be the more reliable piece, and I said that turned out to not be 100% the case. There were some other just weird issues with balancing. Again, it's kind of designing right to the limit. Having, this is what the flow through the boilers are, and we know we've got enough BTUs to overcome, heat up that flow of water. But, we don't have double the capacity that we would need, certainly. So when there were some issues with the balancing, that would show up in the water temperatures, right? If we were to, and that happened a couple of times where just the way that the balancing valve was, it got bumped either accidentally or used as a isolation valve by mistake by people who didn't it wasn't marked and it was sort of misleading how it had been put in. And yeah, that caused problems because, we didn't have twice the capacity that we needed. We had, 1.2 times the capacity that we needed. So, yeah, things like that I think when you lose traditional approach to oversizing covers up a lot of issues because you just have so many BTUs available to you that any little problem, you can kind of just brute force your way through it. When you're actually trying to design properly into size, you no longer have that ridiculous amount of overcapacity that just sort of brute forces through problems. So issues that would probably not show up in a conventional system do show up, and you have to kind of be prepared to deal with them. I think that may be the biggest takeaway, and it's no different. You're designing a central air source heat pump plant for a commercial building, right? Compared to massive 2 million BTU per hour boilers, right? It's the same principle. Heat pump design kind of inevitably comes with this compromise that I'm not going to oversize by double, therefore I maybe don't have that safety margin that I had in the past. So I'm going to notice more issues and have to deal with them.
We probably have time for one more question. Robin?
One question, practical question here from Thomas. Were the gas units boilers or storage water heaters or tankless water heaters?
Effectively tankless. They're boilers, but they kind of function like on-demand boilers. So they're kind of really big tankless boilers would be the best way I could describe them. But functionally, they're more like instantaneous on-demand boilers, but meant to operate without the lag that you see in instantaneous heaters. Like they usually has a bit of a lag as they spin up. So these are designed so that they can instantly meet any load because they've got a little internal storage tank to them. That's the concept. As I said, has had a few issues fulfilling that concept.
I had one more question. It's kind of related to the electric swing tank and the recirc line. Since there's like a significant amount of gas use, would it have made sense to use gas instead of like an electric resistance and maybe add a couple more heat pumps onto the system?
Maybe. I think the storage, I don't know that we could have made a lot of use of, well, not as much use of the heat pumps as we would have wanted just because of the limited amount of storage. We certainly would have been able to make use of them through a lot of the day when there is loads, but what would have ended up happening is that instead of shutting off at 3 a.m., the heat pumps would shut off at midnight because they would have satisfied the load and the whole plant would be sitting idle kind of all night. So, might have, but it also would have been a lot more expensive to do that than, I mean, these electric instantaneous heaters don't cost that much by comparison. So, I certainly won't say it couldn't have been optimized a little bit further, especially with all the performance data that we have now. But I don't think it would have yielded significantly more GHG savings if we had it done that.
Well, that's great. I think it's interesting to just talk about the different trade-offs that there can be in projects and the different design decisions. So I think you both surface a lot of interesting things for the design community to consider. And I hope that a lot of people are thinking that they're going to retrofit some domestic hot water systems going forward.
Yeah. Meter in the winter. That's my advice.
Yeah.
In January. When people are taking hot baths. Okay, so just to wrap up this webinar then, yeah, I really want to thank our presenters, Brad and Harriet, for some excellent insights. Robin, thank you for being an amazing co-host. And I want to thank all of you for joining us. I also wanted to point out two things that are coming up. So we do have a B2E awards about to be released today. So if you are subscribed to our newsletter, it will arrive in your inbox shortly. And also, we are gearing up for a fall in-person event in New West. That's going to be held on October 21st, and it's going to be called Momentum 2026. So tickets are going to be going on sale mid-July, and it'll be a great place for all of us to come and gather, talk about building electrification, and meet your peers. So I hope that a lot of you will be able to join us for that event as well. So again, thank you so much for joining us. We're going to be putting a pause on our Decarb Lunch series for the summer. So we look forward to seeing you again in September. Have a great one. Bye, everyone.